Okay, so let me start in time. I'm very grateful to all of you who stayed till the whatever end. And I apologize, I lost my voice last week, but I get part of it back, so I'll be speaking with less amplitude, but there is amplifier. Today is the last lecture, so I'll tell you some new material, and maybe last third or so I spent on kind of take-home lessons, or what I believe. But of course, each one can encode this course in its own way with its own redundancy. So what we did most of the time so far is that we were counting. Counting and classifying, which is the essence of combinatoric, is considered by mathematicians as maybe the most difficult mental activity, at least very difficult. And there are different, I have a huge temptation to sit on it and just write. Maybe because it's difficult to be fair and unbiased, but it's a really difficult mental exercise. So it's always good to hire somebody to do the job for us. And of course, it was long ago invented. Who is this somebody who can tirelessly and without stopping do the job of counting and exploring probabilities for us? And this somebody is a random walker. So today I'll show you two very different examples of how we exploit the random walker to get some pretty unexpected results. The first will be Google PageRank, and the second would be Yarzynsky relation, or the new form of a second law of thermodynamics, if you wish. Okay? So, of course, in exploiting people, future billionaires were very skillful, and they exploited this random walker to solve the problem which we did not encounter so far, namely, how important is the information? How to quantify the importance of information. And by now, it should not be a surprise that this answer to this question is also solved using statistical methods. And in particular, the question was posed in relation to ranking the pages. Like, imagine we have Borges' library of Bible, and like there are so many books, but then everyone desperate because we don't know what are these precious, most important books. And I won't spend time, even though it's very entertaining to look at first search algorithms, how inept they were before 1997, 1998, when Google PageRank appears. So essentially what we're looking for some vector, pi. So this is a vector with I running from 1 to n, and n is the total number of pages in the internet, or wherever, or books in the library, right? But they all are somehow, in this or that way, partially connected. So we would like to, and we want it to be normalized to be a vector of probabilities, so it's unity. Okay? Now we need to somehow exploring our web to find this vector. And its very natural assumption is that the page, its rank must be proportional to the number of links which come to it, okay? On the one hand. On the other hand, all these links, incoming links to a given page, aren't equal, because some come from a page which has a very high rank, in whatever sense we don't yet know, and some come from other. So what we assume that in this web, which is essentially a graph, which can have many relations, and so if I take this page and there is this link coming into it, it is weighted by 1 over the total number of outgoing links coming from here. Namely, that I assume that pi would be sum over j, pj, which is the rank. This is my I, and this is my j. Okay, and I would sum over all j's. That's what I'll be doing. But each one I take over 1 over nj, where this is 1, 2, 3, nj equal to 3 in this case. Okay? So these two basic assumptions which were made, that every page conveys its rank divided by the number of ongoing links, and of course it does it with its own probability.
So it's always nearest neighbor.
There are no being nearest neighbor in the internet. You're always one click away from whatever site it is, which means that there is no distance here, right? Okay. If this is related to this and it's related to that, it's still one click away. That's important. There's no distance on the graph. Okay. So essentially, you can present it that you have a vector P, which is this vector P times matrix A, right, from the left, right? And your matrix A, ij, it's 1 over nj. And if it's connected, or 0 otherwise. Okay? So that's essentially, which means that what we're actually looking for, it's that eigenvector with the eigenvalue unity of this matrix, which is the connectivity matrix of our graph, weighted by this. And it immediately should remind you the way that we were working with conditional probability for length, which you remember we were saying that pi is equal to pj, pij, or this was actually pj, conditional probability to vj at the condition of j. It's a very similar problem, and I promised you that we return to it, and here we are returning to it again. So this is essentially the same, mathematically speaking, the same exercise as here. And then the idea put forward by two PhD students, and as I already noticed, that all the great discoveries were made by PhD students doing their PhDs, so that's if there are a few of PhD students here. The idea was to make an iterative process, to use a random walk which would explore this web going according to this algorithm. Namely, that we would look P into P as a vector at time t plus 1 as a probability vector at time t. This is all pages of internet times A of t. And A is usually taken time independent for the whole this process. And then the question is, first, is matrix A has an eigenvector with an eigenvalue 1, namely that there is a stationary solution to this equation. And second, if this is the largest eigenvalue. Because if this is not the largest eigenvalue, if there is a large eigenvalue, this process would come to this fixed point. It would be unstable. So we're interested if this is the largest eigenvalue, and we're interested if this is the largest eigenvalue, what is the second eigenvalue, because the second lower eigenvalue will determine the rate of convergence to the steady state. Okay? So that's exactly what was met by Brin and Page, and it's called PageRank algorithm. Of course, Page is here, both a web page and Larry Page last name. So it's called PageRank. And I very much recommend reading the original paper. It's in the open, and it's beautiful, short, and very, very clearly written. And it's funny also.
But in this case, all components of this vector must be non-negative.
Huh?
All components of this vector must be non-negative, right? And if they are
You're stealing from... Absolutely. You are stealing from Larry and Sergey. So essentially,
I'm stealing not from
yeah. Well, from Markov and Frigov, right. So what Leonid say is that, of course, you immediately encounter the problem that in this matrix, there are a lot of zeros. And another problem, which we did not mention, is that there could be loops. For example, you can imagine that you have a disconnected part of internet made of 3 sides. And it's actually, the structure of links is like this, right? So this will be P12 or A12, this is BA21, and this is BA23, and this is BA31. First of all, 3 is egoistic. It does not share its rank, right? There is no outgoing link from here. And second, when this would be very small, you can be caught in this loop and like stay for a very long time in this loop. So these 2 problems you immediately encounter, because your matrix, it has an important property that the sum of every column is unity, but there are a lot of zeros. So you can be really going somewhere and never leaving these places. And then what this PageRank algorithm suggested is that with probability d, which is less than unity, you jump anywhere. Namely, for any given, this is a really random walker now, right? So that's what it actually makes. That's how they exploited a random walker. So you assume that at every step, with a probability d, you have equal probability to jump into any page of the internet, like a random click, which essentially means that they replaced A by the matrix, which is now called G, to celebrate. And this would be dA plus 1 minus d. It's called now teleportation matrix, and originally it was just unities. So this E, it was just E, ET, and this is a unit vector, and this is a unit row. But now, maybe a little bit later, I'll say that you can actually do more sophisticated. It's called teleportation. So original teleportation was like this. Okay. Now all your elements are non-zero, all of them, not non-negative, strictly positive, which is important. Okay. And now, long ago, our 2 brave Californians, they were actually Europeans. In 1906, if I remember right, in 1907, I guess Markov was 1906 and Fred Goldman 1907, who proved the theorem that if you have a matrix of which the sum of every column is unity and all elements are positive, it's called stochastic matrix. We actually are similar to it, but now strictly positive eigenvalues. Then you always have an eigenvector with eigenvalue 1, and it's the largest eigenvalue. And it's kind of trivial to see that you have this eigenvalue 1, because what we know is that Gij, if you sum it over J, it's unity. That you can always say that this is a G times E, right? So E unit vector is a right eigenvector, or it's an eigenvector of GT, but GT and G has the same eigenvalues. So you have eigenvalue 1 for sure, that's guaranteed. And a little bit less trivial step is to prove that this is the largest eigenvalue. This is done using convexity. Again, mathematicians probably easily can immediately see, because you say that if I would have a larger eigenvalue, that would mean that by acting G on this vector, I would get a larger value. That means that I must have at least this sum, some larger value. But the sum of Gij is unity. So if you mixed numbers by coefficient which are as a sum give you unity, you would always have something which is the largest element of this sum. Yes?
I think it's a little more subtle than that, because in principle you can have complex eigenvalues with larger modulus than 1. You have to rule them out too.
Never thought about it. With a strictly positive matrix, you can probably. Yeah.
You can.
Interesting. So tell me, what are the conditions for not having a complex
It's the
eigen?
same. You can prove that they don't.
It means that you can prove, yeah, which means that, right. Well,
You have to work a little harder.
right. That's good to know, because usually I stop at this superficial level because it's not a proof, it's rather kind of a hand-waving demonstration that first there is such an eigenvalue, and kind of convexity argument give you hints that it must be a largest eigenvalue. So if you have this A, your original matrix, and it has eigenvalues 1, lambda 1, lambda lambda 2, lambda n, then G would have 1, lambda 1 d, lambda 2 d, etc. As long as my teleportation matrix is kind of taken trivial like this. At that point, Sergey and Larry encounter this problem. So what actually to take is D, right? This probability of teleportation. Because if you want a fast convergence, and you do want fast convergence, right? Not only because of instant gratification, but it's, because the bots of Google, I mean, they troll internet all the time, getting these numbers, and it's a big and expensive job. But eventually, if you take D very large, then you totally disrespect the actual structure of internet, which is encoded here, right? So eventually, and it still stands, they took D, which is 0.25. Yes, if I'm not mistaken. This more or less based on a statistics of how often people use their bookmarks, etc. And of course, this is the simplest algorithm in the sense that you can make it individual, and which is, by the way, every person can actually do it. So you can take here V, which would reflect your own kind of logs of searches and goings, and then you would have your own individual rank for this. And that's more or less sometimes now. Of course, I don't really want to go into how it all went down in the last, I don't know, 10 or 15 years. It's actually do not work as good as we would like it to do, but that was a huge breakthrough. There were other people who were doing similar things at the same time. Well, this more or less shows you how you can exploit random walk to get something which is truly precious, namely the vector of ranks. Okay, questions here? Maybe advices from better educated people. Okay, then let's go and consider a second exploitation of a random walker, which is somewhat more trivial and more non-trivial. So let's now go from graph to really simple situation, one-dimensional random walk. So I'm on a line, or actually even on a discrete set of points. Okay, so now my I just runs again from 1 to whatever n. And I have a random walker which just randomly goes right or left with equal probabilities. Just, Drunkard's standard problem. So I would say that my pi at time t plus tau, which is the tau time of my jump, is just 1/2 of pi minus 1 of t plus p of I plus 1 of t. That's a standard situation. Then, of course, I would, if I'm interested in the change, then I would take the difference, t plus tau minus pi of t, and it asymptotically would go into dp dt times tau, and it is equal to the second difference over here, pi of t I plus 1 plus pi minus 1 minus twice pi of t, and it would go into second derivative. So I will get a diffusion equation. Okay, that's just kind of more or less a standard random walk. Now what I'll do to this random walk, and following Chris Yerzhinsky and many other people who are actually doing it, I'll put this random walker into an external field, which means that apart from this diffusion, isotropic left to right, I would also have some kind of external potential, which will be V of x. And it would impose a velocity on my a drift on my particle. So now I would make it continuous. This would be x. And so x dot would be my v, which would be minus dv dx. It's a kind of Aristotelian world in which a force creates velocity, namely that it's, technically speaking, it's an overdamped small particle. More or less, it describes most of our situation. It could be generalized pretty straightforward into a particle with inertia, but we assume that there is no inertia, force proportional to velocity. Okay? And in this case, if I'll be interested in the probability density on x as a function of t, which is essentially my p divided by whatever lattice size I had before, then this d rho dt, as we discussed back when we discussed dynamical chaos, is always divergency of j of a current in my x space. And in this particular case, it would have two elements. One would be the diffusion, which is due to this process, and another will be d dx rho times v, my velocity, over here with a sign minus, which will be dv dx. It's called Fokker-Planck equation. It describes the random walker in a drift. And the drift is non-uniform, namely it's imposed by some field. Now, this solution, this equation has a stationary solution, which is just a usual Gibbs probability distribution. It's this rho naught, let's call it, because it's a stationary thermal equilibrium. And it's and t is actually a factor over here. So here z naught is a partition function, namely just a normalization. So it's an integral exponent minus v of x over t dx. And it's, of course, a function of temperature. OK? So yes?
How was capital T defined?
It's just defined essentially as a diffusivity. This is the diffusivity in this X space. So when you do all this expansion, what you would get here a squared, you see? And here you would have time, tau, which is time of jump. This is the space of jump. Then you go into continuous limit, and you consider limit. I wanted to skip it, but it's good that you asked. You go to limit, tau goes to 0, a goes to 0, but a squares over tau goes to a constant, which is this constant up to 2 pi or 4 pi or whatever. Okay, so that's the way that you define diffusivity, which is essentially it's related to temperature, because for Brownian particle it comes because you have this thermal agitation by okay. So now for equilibrium, namely for v, which is dependent only on x, there is also a very powerful statement which is called detailed balance. And it's something which is not only relates to a probability of b in the point x, it's given by this formula, but to this conditional probability with which we always obsessed. What is the probability of come here if you were before there? So if you're interested in the probability of rho transition from x x0 to come to x prime at t prime at t, yeah, this is 0, this is t. Okay, so you're interested in this quantity. Then you may ask how it's related to the inverse probability of being initially at point x prime, but instead come to the point x at time t. Okay? And the answer is that if there would be no v, these probabilities would be equal, because all places in x are the same. But now v skews it. V makes you your probability very non-uniform, right? So where v is larger, your probability is smaller. And where v is smaller in the minimum, that's where you actually live most of your time. So the statement is that you need to weight it by the probability of a starting point. And this is called detailed balance. Okay? And that was all classical science, long known. And somehow, many people, myself including, believe that that's more or less how much you can get out of this potential. Because if you are starting to think about this being a function of x and t, you can't say anything. Because now, your probability distribution apparently is not this. You cannot put here t. Because if you plug it into this equation, for example, then when you differentiate this, you would get d rho dt will be everything else which cancels out of this. But there will be one term when you differentiate in this exponent v. So it will be term which would be proportional to dv dt 1 over z and 1 over t, right? So this would be n times rho. Okay, and that immediately shows that this is not a solution. Of course, when you change potential, it's not immediately that your distribution reflects it. And there generally was a despair, and I remember myself thinking about it sometimes at maybe late 80s, that for infinitesimal thing near equilibrium you can do something, but not arbitrarily far from equilibrium. And that's what actually great Yerzhinsky taught us, that you can do however far from equilibrium you are, you can actually derive a very beautiful exact relation, which we now interpret as a new form of second law of thermodynamics. And to do it, you need to consider the following thing. You need to weight your distribution, namely, but what you weight it for? Let's introduce a quantity which we'll call work. It's not a function, it's a functional of time, so I will put as mathematicians prefer to do it, not as an argument, but as a subscript. So it's an integral from 0 to t over time, dt prime, of a quantity which is dv over dt. And what this partial derivative means, that this is a function of x and t. But you take it on the trajectory of a particle, which follows the equation x dot equal minus dv dx plus random noise. Okay? It is this equation which gives you this Fokker plan. This is its kind of dynamical counterpart. So you take it on at t prime, at t prime, at t prime. So it's not a total derivative which comes out because your particle goes, but only because it comes out of an external change of a potential. It's essentially the work done by external forces which change the potential. And I did not have time. I wanted to show you how people actually experimentally proved Landauer's conjecture considering such a particle and manipulating by optical tweezers the potential in which this particle existed. If you're interested, you can look in the lecture notes. There is a detail. There are 2 Nature papers which are very beautiful and exploit this setting. So we'll consider this W. And what we'll do now, we'll use it in the following form. We'll weight our rho by this quantity. Okay? So we consider now a more general object, namely that rho is now a function of x, w, and t. Okay? Which means that for this is a random quantity which depends on this random trajectory. And now I consider a joint distribution of x, w, and t. And it would have the following form. It will be, again, having this form, but now I have extra direction in my space. I have x and w direction. So I need to add to my two parts, which is a motion along x by diffusion and by drift. I need to add the motion along w, if my sign is right, yes, rho, and apparently the derivative of this is just the derivative of z. So it will be dv dt. And the sign minus come, yeah, because it's plus m. Okay? So this is a new equation which describes the joint probability of being in a point x and suffer energy change of work, external work w. Okay? And it's again a random variable depending on trajectory. Now you see that here I would have a term which will be exactly like this term. So now it would cancel. Namely, that if I would now consider function which is an integral of a w of rho e minus beta w. Beta is 1 over t, will be always. So which means that I'll take this equation and integrate it over all w. So, and of course I did not get this because I first multiply it by an exponent and then I integrate it. So when I integrate it over w, all this disappears. And this would give me, by integration by parts, this d over w would act on this exponent. Where is this my exponent? Yeah, this exponent. And as a result, I would get df dt is equal to t fxx, that's all unchanged, plus t over 2, plus ddx x dv dx. And what I will get is that minus beta dv dt, okay, f. So out of this, by integrating, I get for this function f, which is my probability distribution, average over all works, but every work weighted by its own exponent. The meaning of this, of course, it's a phase volume. The change, this work done, it's work divided by temperature. It's a change of a free energy, and like a change of entropy. An exponent of it is a phase volume. Namely, I weight my probability now at every moment of time by instant value of phase volume, which depends on how much work I did, compressing it or expanding. So now this, of course, has an exact solution, which is f equal to exponent minus beta v of x t at every moment of time. And of course, it has a normalization factor, zt, which is exponent, which is an integral minus beta v of x t dx. Indeed, if you take this, substitute it here, this term would cancel this term. Okay? So essentially, you found Gibbs solution, but for a quantity which is, it's not a probability distribution, right? It's kind of some weighted probability distribution integrated over everything. And you can, of course, now, it's f of x, right? Even though it's not a probability distribution, you can get many beautiful things out of it. Fluctuation dissipation theorem, all its descendants, namely for whatever high moments, for 4th, 6th, 8th moments, you can get all this beauty just expanding this function. It's a very, very powerful instrument, but I'll just show you the first integral of it. So let's just integrate it, this guy. Okay. So if I integrate f of x t dx, and remember that f is this quantity, right? It's an integral over dx dw rho exponent minus beta work. Okay? It's essentially exponent minus beta w mean value as a function of time, any moment, whatever complicated. And of course, when I now take this and I integrate, yeah, somewhere I made, yeah, this is what I was too fast and you did not stop me, is that I did not show you the boundary condition for this equation. So this was equation for now in the space x and w, and I need to set a boundary condition at x, w at time t. And what I need to assume, what I assume, at least what Yerzhinsky assumed, that this is the Gibbs distribution at time 0 divided Vatan over z0, and it's a delta function of w. Namely, because just by definition, my work is an integral from 0 to time, so at time equal to 0, my work was 0. Okay? So with this condition, this solution is actually like this. It has a right boundary condition, and then when I integrate it, the integration of this would give me zt, and that would be z naught. One can also write it, of course, it is an integral dx exponent minus beta v of xt. There are too many formulas, but we'll stop in a moment and we reflect and meditate looking at it. Or you can also write it as a where this is a free energy, right? The partition function is an exponent of a free energy. So let's reflect what did we do. We started from the initial distribution. Here is our initial distribution, which was Gibbs at a given potential. Then we started to change this potential in whatever arbitrary way we want. And then what we proved is that such an average for at any instant of time, such as average, just determined by the differences of free energy taken at this finite moment of time, as if it would be at this point equilibrium distribution. Of course it is not, right? Because it needs some time then to relax. But this time of relaxation would not involve further work and change of phase volume. So essentially it tells you that such an average on however non-equilibrium evolution is completely determined by the finite and initial value of its free energy, which tells you that if you rightly weighted your probability distribution in the right weight, it is this exponent of this work. On the other hand, it tells you that if you want to measure something which is equilibrium, you don't even need to be adiabatic. You can go very fast. It is just you make changes, which is pretty fast here. As long as you compute this average, it would give you this difference in the free energies. So in a sense, it's a very, very powerful statement. And now why we call it a second law of thermodynamics? Because when we write it like this, let's take all this and put it here, right? So what we have? We would have exponent minus beta. Let's put t in the denominator. Where is my eraser? Yeah, okay. Don't see it. So if I take it w plus delta f over t equal to unity, it's an exponent of minus delta s equal to unity. Okay? So essentially, what did we have shown is that for arbitrary non-equilibrium process in this very, very simple system. Now go generalize it. Well, Misha did some jobs, there's other people, but it's still complicated. But it shows you something very powerful, very technically simple, relatively, right? And totally unexpected, that you can cast your second law of thermodynamics, which is delta S larger or equal than 0. This is a consequence of this, but not other way around. This is more powerful statement, right? So what we have shown that there is actually equality behind the inequality of a second law.
The mean of
Thank you. It's always good somebody watching. Before we mentioned it, that another way of casting second law of thermodynamics, not as a way to say that Boltzmann entropy grows, but as a way to say that Liouville entropy is conserved, and because you have a growth of mutual information generally, or non-decay, and mutual information is non-negative, then also additive part, which is Boltzmann entropy, must grow. This is another way to cast second law of thermodynamics as an equality rather than inequality, right? And of course, there is it's a big, you just go Google it and you'll see how many very non-trivial things written in it. But even this most basic stripped down version tells you that you take a simple one-dimensional particle in a time-changing potential, you weight its distribution in the right way, and you obtain exact equality. And whatever, you know, this is just convexity of exponential function, which is exploited here. You can do many things with it. And the last thing is even more general statement, which I'll give without any derivation or proof, just to kind of let you to see a bigger picture. Again, it's all came out of trying to generalize these things, right? It is this understanding that you need to weight it by exponent, which goes back, of course, to this basic equilibrium detail balance. And then, again, for a very particular class of system, they were formulated the following relations, that if you take a probability of having in whatever process a change delta S, and you would be interested in the probability of a backward in time, I would call it like this, of a process which has a minus delta S, okay? Then there is a relation between them which look like this, which is kind of a generation of this exponent minus delta S. This is again, it's a very particular classes and you can prove it. Why it's more general? If you integrate it now, if you integrate it over d delta S, namely you take an average of minus delta S, which would be unity, then your right-hand side would be exponent minus delta S equal to unity, right? So the integral of this relation is this relation. But it's more powerful because it's a detail of it, right? It's like this is the first moment of it, of convexity, but this is actually the integral of this, which is even more powerful. And this is something which, I mean, came truly unexpected. And I think that it opens our eyes to the possibility that in a relatively simple technical means, 150 years after, you know, classical Boltzmann and stuff, you can generalize basic statements about second law of thermodynamics into something which extends it very much into a domain of away from equilibrium. Of course, there is a technical, commercial, engineering part to it. We really started to be interested in such quantities. We are working with small particles. They do fluctuate. The probability of this is vanishingly small for macroscopic system. There is no probability that for macroscopic system you would see that entropy would actually decrease. But for nanoparticles, this is a measurable probability. So this is not only a pure mental exercise. This is a big engineering which is behind it. But when I look at it, from the viewpoint of fundamental physics, it's really something which I think it's very important, and it led us to look at it, and again, the same basic informational thing, which is the change of entropy. Questions? Yes, Misha?
Well, comment, if you allow.
Sure, of course.
Maybe you can elaborate. Well, your explanation of Dzerzhinsky is, as you said, you don't need to wait, right? So you don't need to equilibrate, and you can have very fast. And initially that excited a lot of people, experimentalists, those who experimented with polymers, for example, but then they run into a kind of conundrum, which I don't know if there is a way to overcome. Averaging means very different things. So if you do it adiabatically, only one sample is enough. But if you do it fast, the faster you do, the more samples you need.
No free lunches, of course. Yeah.
So is there a way to bypass it?
It's first of all, you cannot kind of fool the nature, but of course, there is a very interesting problem of optimization here, which different people, but I know Krzysztof Gawecki, for example, work on it, is actually how you can balance this, that you want to do it as fast as possible, but still do as few as possible sampling size. So there are always a trade-off and differences.
It's and then I didn't follow. So is it, and it's exactly as you said. So order one type of thing, right? I mean, maybe optimal is.
I did not follow. I did not know if there were any breakthrough of fundamental nature, but there was some kind of reasonable kind of balance statement. Yes, Alan.
Is there a way? There surely must be experiments that you could test that.
Yes.
You're asking.
Yes.
Yes. Entropy
yes.
increasing.
Yes.
The probability of an increase.
There were hundreds. There were hundreds. Well, maybe tens, but many tens. People in Lyon did really very beautiful experiments. It's usually done by optical tweezer. Again, very similarly to the way you check Landauer, namely that because you know your potential, it's optics, right? So you know your potential, you can exactly compute this integral. This is something that you compute. Now what you need to do, you need to follow your particle, really, to see where it is, because you change potential, but particle, because it's under thermal noise, it somehow wanders. So you need to follow it. So you disturb the system. It's a non-trivial job. People got already prizes for it. I mean, really, it all, like Misha said, was maybe 15 years ago was a boom of it, but it's still people working. It's now much more non-trivial things that they are working with it, but it's essentially the same setting. So you do very non-equilibrium evolution. They always ask me, can you do it for turbulence? And the answer is no. It's essentially the system is under thermal noise. It's some detailed balances somewhere here. There are only 1 or 2 or 3 degrees of freedom which are deviated from equilibrium in a trivial way, in a controlled way, right? You deviate system from equilibrium essentially by dynamical quantity which has 0 entropy. It's a lot of things which hidden here which does not allow us to use it in turbulence, unfortunately, even though I spent several years trying. But still, I find it very inspiring. It's really. Yes, Michel.
On this question of Alan, I know of experiments 15 years ago with polymers, right? Stephen Chu, right?
Yeah.
He actually initiated that. I think Bustamante from Berkeley.
Yes. Sergio Ciliberto did it, yeah. There are several people did it.
15 years ago. So and you mentioned now turbulence, right? So I actually don't know of any turbulence type of experiments.
Of course. What's the first thing we do? We said, forget the equation. Let's just take something like this and measure it in turbulence. And we spent with Eberhard, Badin-Schatz, and with Mr. Schatz a lot of time just analyzing the data and looking for something like this. And we did not find it. Nothing that I would find physically interesting. So we were trying to do phenomenological things, and it did not work.
What actually quantities did you use to measure?
We didn't know. We were looking for different quantities.
Yeah, we never know what
Yeah.
you actually
For example, we were looking at just a particle in a turbulent flow. The question that we ask, for example, okay, here is a particle. Okay, it does some idiotic things. You ask if it's a turbulence or it's just thermal noise. Well, you immediately see it's not a thermal noise. It has kind of a longer correlated motion. But then, I mean, with Misha long ago and with other people, when we use the passive scalar, we actually proved that in the incompressible flow, the statistics is reversible. So how would you know that it is in turbulence? And we eventually found the way to know. You need to get something like, you know, a work done on it, energy change, and it's asymmetric. So it's very similar. And then we ask, is there any exact relation like this? We did not find it. But we found the way to measure irreversibility and related to Reynolds number. So we were very much inspired by this. There was some 7 or 8 years ago. It's called flight crash, I don't know, somewhere Nature Communications, I guess.
Grisha, and anybody
PNAS.
tried to do it in this simpler wave turbulence?
Good question. No, no. That may be something that could be
It's
explored.
quite interesting in the wave turbulence context because, for instance, like in waterways, the energy and particle all go in at very high wave numbers, and so you have
Yes, here is a.
this wrongly wave cascade for energy for a little while, and then you get so yeah.
Alan, Volodya, wait. I mean, you speak simultaneously. Alan was saying that in wave turbulence, there must be something of that kind. And essentially what we found that you find the reversibility, at least what we found for hydrodynamic turbulence, that the particle slowly builds its energy and then loses it fast. It's a kind of analog of cascade. Now, Volodya, what you were talking, please go ahead.
About fluxes of energy.
Yes, essentially all this must be related to the fact that you generate it slowly and you lose it fast. This is counterpart that you go from large scale to small scales. By the way, inverse cascade totally outside of such framework. But we did not find any exact relation. We found some qualitatively beautiful things like irreversibility expressed in terms of, you know, building slow and losing fast. That's what I called flight crash events. But for wave turbulence, nobody actually explored it. This is a very interesting idea. I think that we need to do it someday. Okay, are there any other questions, or we can now try to wrap it up and reiterate? Yes, Misha.
Maybe I was waiting for you to discuss configurational entropy. You don't want to do it.
I just don't have time for it. You know, there are so many things that I really wanted to. You know, I skip all the normalization group. I skip many other things, and in particularly, you know, a price of information and all this. Anyway, let me try to wrap it up and just give you again, because there are people here who know some things better than me, and there are different things. So what I really want to give this panoramic view, which I believe is pretty simple, and it's the following things: that what started from this, let me remind you, from a very fundamental observation about a genius Frenchman, that this is, if you look at these two quantity, there is something over T, right? There is something relation. So it's really something which started from trying to understand what are the limits of a thing we can do by burning things, how much work we can do out of burning things. Essentially, without much change, at least conceptually, went into answering the question how fast we can transfer information from here to there, or how much we can get out of measurements. And then it went more or less seamlessly to the asking questions how fast we can compute, or how slow we can compute, how much we need to burn if we are computing. And then when we go and ask how actually we can drive a driverless car, namely how fast we can proceed information and encode it in the most compact way. And then when we ask how actually living beings do that when they look at something or do something, we encounter essentially the same quantity, which is mean logarithm. I think that this is, I mean, if you try to boil it down to the simplest, like Newton said, it's useful to solve differential equation. Simple messages are very powerful, right? So what my take-home lesson from out of all this, you always average logarithm. Just look what logarithm to average. If you find the right logarithm to average, the rest will be technicalities. Okay. So if there is a message here, it is this. Okay, technical message, like to researcher, not philosophical. And philosophically, of course, what I find really amazing and also very frustrating is why it took so much time. Because I really remember myself sitting when I was undergrad and listening about all these paradoxes of statistical physics, and I hated every moment of it. I just remember it. And then I asked why everything, why the things which were more or less evident to Maxwell when you read his diaries about all this knowledge, probability, it took so much time. And my own explanation is that there still are people who very much fighting to keep scientists out of science. There are really people who believe that this is something which is kind of totally objective in some very 19th century philosophical meaning. And I have a great scientist who took this course 2 years ago when I was given it, and he ran to me and asked, Grisha, are you saying that second law of thermodynamics is not a law of nature? I said, in what sense? I asked him, it's not like law of gravity of quantum mechanics, not the law of nature. And say, no, it's not a law of nature, it's a law of our understanding or misunderstanding or lack of knowledge of nature. But are you sure that the laws of quantum mechanics are not the laws which are designed by humans for humans and actually work this way? And I think this is something which is really profound and psychologically very difficult for us to understand that what we are doing is good and working sometimes, but it's something that we designed for us by us. But the moment we understand it, it really opens a lot. Okay, so if there are any remarks or questions, please. If not, then thank you. Yeah, please.
I have one remark. In addition to averaging logarithms, I would not forget about exponentials.
Yeah, convexity. Technical, it's not necessarily exponential, but the general idea of convexity, it's, of course, of which logarithm and exponent are two examples, but it's actually even more powerful idea, right?
If you look at the board,
everything is, so it's exponential, like your maximum is always on the boundary. That your convectivity gives you this thing, right? So there are several, and if you look at lecture notes, there are 16 take-home actually lessons. Everyone like one sentence, but it's not 2, it's 16, but maybe it's too much. So you can question.
I have a general question for my friend. He asks, how do you use the Kolmogorov complexity to see structure in data for financial time series or data in general?
Yeah, I did not mention complexity, which in a sense is a close relative to the entropy, but this is something else. It's a kind of a shortest line, a code by which you can encode this. And on average, it's usually equal to, but it's something which it's a very powerful idea, but I did not even mention it. And I did not even mention Kolmogorov entropy, which is another way to learn things looking backward in time. What can I say? There are, Cover and Thomas, great book on, elementary, but very well written. But it's really like this, right? So it's a 1-year course. That's where you look at.
Which incidentally is going to be taught here probably next year.
Excellent. This is essentially. Congratulations. Then you would get what actually. Well, okay. If there are no other questions, thank you again. I enjoy every moment of it. And thank you for patience. Yeah.